You want me to explain gravity? Well, here's the problem. I can't. Nobody can. We can describe it beautifully, calculate it precisely, but if you ask me why gravity exists, I don't know. And neither does anybody else. But let me tell you what we do know and why most of what you learned in school is a little bit wrong. People say gravity is a force that pulls things down. Okay, but what does that mean? You're not really answering the question, you're just giving it a name. It's like saying, why does the chair stay up, and answering because it's solid? You haven't explained anything. You've just attached a word to a phenomenon. And that's fine for everyday life, but it's not physics. Physics is about understanding what's actually happening. So let me start with what you probably learned. Newton told you that every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. Beautiful equation. Works wonderfully. You can predict planetary orbits, calculate trajectories, send rockets to the moon. The math is elegant and precise. But Newton himself knew there was a problem. How does the Earth know the moon is there? How does the sun reach across 93 million miles of empty space and pull on the Earth? What's doing the pulling? Newton didn't know. He admitted it quite honestly. He said he would not make hypotheses about the mechanism. He gave you the rule, the mathematical description, but not the explanation. And for 200 years, that bothered people. It bothered them a lot. Now, here's what Einstein figured out, and this is one of the most beautiful ideas in all of physics. Gravity isn't really a force at all, it's geometry. Space itself is bent, curved, warped by mass, and objects, they're just moving in straight lines through curved space. You see, when you throw a ball, it travels in what looks like a curve to you, but from the ball's perspective, it's moving perfectly straight. It's the space around it that's curved. Think about that for a moment. The ground you're standing on, the chair you're sitting in, you think you're stationary, but you're not. You're accelerating upward. The Earth's surface is pushing you up through curved space-time. That's why you feel weight. Not because gravity is pulling you down, but because the ground is pushing you up, preventing you from following your natural straight line path through curved space. And this isn't just philosophy. This is measurable. In 1915, Einstein predicted that light from distant stars would bend as it passed near the sun. In 1919, Arthur Eddington measured it during a solar eclipse. The stars appeared shifted exactly as Einstein predicted. Space was bent. The prediction was confirmed. But here's what bothers me about how they teach this. They show you a rubber sheet with a bowling ball making a dip and a marble rolling toward it. And they say, see, that's gravity. But wait a minute. Why does the marble roll down into the dip? Because of gravity pulling it. You're using gravity to explain gravity. That's no good. That's circular reasoning. The rubber sheet analogy works only because you already have gravity pulling things down toward the sheet. It's a useful visualization, sure, but it's not an explanation. It's a picture that relies on the very thing it's trying to explain. You know, there's something Galileo figured out 400 years ago that people still get wrong. Heavy things and light things fall at the same speed. Drop a hammer and a feather in a vacuum, they hit the ground together. We did it on the moon. Commander David Scott, Apollo 15, 1971, he held a hammer in one hand, a feather in the other, dropped them simultaneously. They landed at exactly the same time. 400 years after Galileo, and we had to go to the moon to prove it to people who still didn't believe it. But ask someone on the street today, they'll tell you the heavy one falls faster. They'll say it with complete confidence, because that's what experience tells them. Drop a hammer and a feather on Earth, and yes, the hammer hits first. But that's not gravity, that's air resistance. The feather floats because air pushes on it. Remove the air, and there's no difference. None at all. Every object falls at exactly the same rate regardless of mass. And that tells you something profound about the nature of gravity. You see, in Newton's physics, heavier objects should fall faster if gravity is a force. More mass means more force. But they don't fall faster. Why not? Because gravity isn't pulling on the mass. It's curving the space the mass moves through. And all objects follow the same curved path through space, regardless of how much matter they contain. A planet and a photon traveling through the same curved region of space follow the same geometry. Now, here's another thing people get wrong. They think astronauts float because there's no gravity in space. Nonsense. Complete nonsense. At the International Space Station, orbiting about 250 miles up, gravity is almost as strong as on Earth. Maybe 90%. The astronauts aren't floating because gravity disappeared. They're floating because they're falling. The station is falling. The astronauts are falling. They're all falling together around the Earth. You don't feel gravity when you fall. That's Einstein's big insight. That's the equivalence principle. You cannot tell the difference between floating in deep space with no gravity and falling freely in a gravitational field. They feel exactly the same. If you're in an elevator and the cable snaps, for those few seconds before you hit the bottom, you're weightless. You float. Your stomach floats. Everything floats. You can't tell in those moments whether you're falling on Earth or drifting in interstellar space. There's no experiment you can do inside that elevator that would tell you the difference. And that's not obvious. But it's true. Think about what this means. Gravity doesn't push or pull. You feel weight only when something prevents you from falling freely. Right now, the ground is pushing up on you. The chair is pushing up on you. Remove that support and you'd be weightless instantly. Not because gravity stopped, but because nothing would be preventing you from following your natural path through curved space-time. And here's something else that'll cook your noodle. Gravity doesn't act instantly. Nothing does. Einstein showed the speed of light is the ultimate speed limit. Information cannot travel faster than light. So if the sun disappeared right now, poof, gone. We wouldn't know for 8 minutes. We'd keep orbiting nothing. The Earth would continue on its path as if the sun were still there, until the information, the change in space-time curvature, reached us traveling at the speed of light. In 2015, we detected gravitational waves for the first time. LIGO, the Laser Interferometer Gravitational Wave Observatory. Two detectors, one in Louisiana, one in Washington State. They measured ripples in space-time itself from two black holes that collided 1.3 billion years ago. The black holes, each about 30 times the mass of the Sun, spiraled into each other, merged, and sent out ripples in the fabric of space. Those ripples traveled across the universe for over a billion years and arrived at Earth on September 14, 2015. The detectors measured a change in distance smaller than 1/10,000th the width of a proton. Think about that. They measured space-time stretching and squeezing by an amount so small it's almost meaningless to say, but they measured it. And it matched Einstein's predictions perfectly. Einstein predicted gravitational waves in 1916, almost exactly 100 years before we detected them. The theory works. But here's what keeps me up at night. We have quantum mechanics. Beautiful theory, works perfectly for atoms, light, photons, electrons, everything small. The predictions are accurate to 12 decimal places. 12. It's the most precisely tested theory in the history of science. And we have general relativity. Einstein's gravity works perfectly for planets, stars, galaxies, black holes, everything big. Also incredibly precise. Also incredibly well tested. But put them together? They don't fit. They contradict each other. At very small scales, quantum mechanics says particles can be in multiple places at once, can tunnel through barriers, can be entangled across vast distances. But general relativity says space is smooth, continuous, deterministic. The two theories speak different languages. They make different fundamental assumptions about reality. And when you try to apply both at the same time, when you try to describe very small regions of very intense gravity, the math breaks down. It gives you infinities, nonsense answers. Near the center of a black hole, inside the singularity, or at the very beginning of the universe, at the Big Bang, you need both theories. But we don't have a theory that combines them. We don't know how to make them work together. So one of them, or both, must be incomplete. They're both right in their domains, but they can't both be the fundamental truth. Something deeper must be going on. String theory tries to solve this. Loop quantum gravity tries to solve this. Other approaches exist. But we don't know yet which one, if any, is correct. We're still looking. You see, this is how physics is. You discover something beautiful, you test it, it works wonderfully, and then you find something you cannot explain, some place where your beautiful theory fails. And that's not a problem. That's the frontier. That's where the next discovery lives. Now, let me tell you something practical. GPS satellites, the ones that tell your phone where you are, they have to account for relativity, both kinds. Special relativity because they're moving fast relative to you, which makes their clocks run slower, and general relativity because they're higher up in Earth's gravity well, which makes their clocks run faster. If you didn't correct for both effects, GPS would drift by miles per day. Your navigation would be worthless. So every time you use GPS, every time you check your location on your phone, you're relying on Einstein's equations. You're using general relativity. It's not abstract theory, it's engineering. It's how the world works. But why does mass bend space? I don't know. Nobody knows. We can describe it mathematically. We can measure it precisely. We can predict its effects with astonishing accuracy. But the mechanism, the reason, the why, we don't have that. We have a beautiful mathematical description, that's all. And maybe that's all we'll ever have. Maybe why is the wrong question. Maybe the universe doesn't have a reason. Maybe it just is. Maybe the job of physics is to describe how things behave, not to explain why they behave that way. Maybe asking why is like asking what sound the color blue makes. It's a category error. The question itself might not make sense, but I don't think that's quite right either. Because we've asked why before and found answers. We asked why the sky is blue. Turns out it's because air molecules scatter short wavelengths more than long wavelengths. We asked why objects have mass. Turns out it's because they interact with the Higgs field. We asked why antimatter exists. Turns out it's a consequence of combining quantum mechanics and special relativity. So sometimes why has an answer, but sometimes it doesn't. Sometimes you reach a level where you have to say, this is how the universe is, and we don't know why. Maybe mass bends space because that's what mass does. Maybe that's the fundamental property of mass, and asking why is like asking why does 1 plus 1 equal 2? Because that's what addition means. You've reached bedrock. You can't dig deeper. Or maybe we can dig deeper, and we just haven't figured out how yet. Maybe in 50 years, or 100, or 1,000, someone will discover the reason mass bends space. Maybe they'll find a deeper theory that makes general relativity obvious, inevitable, the only way things could possibly work. Maybe. You know, Isaac Newton discovered his law of gravity in 1687. For 228 years, it was the best theory we had. It worked beautifully. And then Einstein came along and said, no, it's not quite right. Here's what's actually happening. And Einstein's theory has now been tested for over 100 years, and it works beautifully. But maybe in another 100 years, someone will come along and say, no, Einstein wasn't quite right either. Here's the deeper truth. And maybe that theory will last 1,000 years, or maybe it'll last 50. We don't know. We can't know. Science doesn't give you final answers. It gives you better and better approximations of truth. And that's okay. That's the fun part. Anyone who tells you they fully understand gravity is either lying or selling something. The honest answer is we know a lot. We know how to calculate gravitational effects with extraordinary precision. We know how to use gravity to navigate spacecraft, to predict eclipses, to find exoplanets orbiting distant stars. We know it's not a force but a curvature of space-time. We know massive objects create gravitational fields, and those fields can produce waves that ripple through the universe. But we don't know why. We don't know how gravity fits with quantum mechanics. We don't know what happens at the center of a black hole where the curvature becomes infinite. We don't know if space is quantized at the smallest scales, broken into tiny discrete units, or if it's truly continuous all the way down. We don't know if there are extra dimensions we can't perceive. We don't know if gravity leaks into those dimensions, which might explain why it's so much weaker than the other forces. Gravity is about 40 orders of magnitude weaker than electromagnetism. 40? That's one with 40 zeros after it. Why is gravity so weak? We don't know. Maybe it's leaking into extra dimensions. Maybe there's something about the structure of space-time we haven't figured out yet. Maybe we're asking the wrong question. But here's what I love about this. Here's what makes physics beautiful. We admit what we don't know. We're honest about the limits of our understanding. We don't pretend to have all the answers. Science isn't about certainty, it's about curiosity. It's about finding things out. And with gravity, there's still plenty left to find. The pleasure is in finding things out, not in pretending you already know, not in accepting easy answers that don't really explain anything, but in looking at the universe with honesty and saying, I don't know, but let me try to figure it out. Let me do an experiment. Let me test a prediction. Let me see if the math works. Let me measure it and see what happens. And when the measurement doesn't match your expectation, when the experiment gives you a result you didn't predict, when the universe surprises you, that's not failure. That's discovery. That's the universe telling you something new. That's the moment when you learn something nobody knew before. Einstein didn't know gravitational waves would be detected. He thought they'd be too weak to ever measure. But he worked out the math, made the prediction, and 100 years later, we built detectors sensitive enough to see them. We found the waves. And now we use them to observe the universe in a completely new way. We can see colliding black holes, merging neutron stars, events that produce no light but shake space-time itself. That's what science does. You make a prediction from a theory, you test it. Sometimes you have to wait 100 years for the technology to catch up, but eventually you test it. And if the prediction is right, the theory survives. If the prediction is wrong, you learn something even more interesting. You learn the theory is incomplete. You learn reality is stranger than you thought. Gravity is strange. Mass bends space. Time runs slower near massive objects. Light follows curved paths. Objects in free fall are weightless. And standing still on the ground, you're actually accelerating upward through curved space-time. None of this matches your everyday intuition. None of it feels obvious. But all of it is true, and we know it's true because we've tested it. We've measured time dilation with atomic clocks. We've photographed starlight bending around the sun. We've detected gravitational waves from colliding black holes. We've used general relativity to make GPS work. The theory has been confirmed thousands of times in dozens of different ways. So we know something. The theory works. General relativity is correct, at least in the domains where we've tested it. But why does mass bend space? I don't know. Nobody knows. And that's okay. That's not a failure. That's where we are. That's the frontier. Maybe someday we'll know. Maybe we'll find a deeper theory that makes it obvious. Maybe we'll discover that space isn't fundamental, that it emerges from something more basic, and the curvature is just a consequence of that deeper structure. Maybe. Or maybe we'll never know. Maybe this is as deep as it goes. Maybe mass bends space because that's what the universe is, and there's no deeper why. Maybe we'll just get better and better at describing it, calculating it, using it, but we'll never really understand it. And honestly, I'm okay with that. Because the universe doesn't owe us an explanation. It doesn't have to make sense to us. It doesn't have to match our intuitions or satisfy our desire for ultimate answers. It just has to be. And our job is to figure out how it behaves as best we can, with honesty and rigor and humility. That's science, not certainty, not final answers, just better and better questions and the joy of finding things out.